dimensional because n is finite. Suppose I give you these finite dimensional probabilities. Which conditions they have to satisfy to implement a single measure? Of course, there are some compatibility conditions. For example, if I integrate over the last variable of Tn, I must obtain the preceding. These are the famous Kolmogorov conditions. Okay, these are given on the joint probabilities. However, in non-commutative case, there are no joint probabilities. Because the non-commuting observables have no joint probability. So we do it with moments. And this is the reconstruction theory. Well, how to translate the compatibility condition on the moments. Okay? And then you do non-commutative, and then you prove that given when you have the moments, you can automatically obtain the correlation functions, because a correlation function is a special moment, and therefore you apply kind of GNS construction, and you get Hilbert space and the representation. This is the idea of the reconstruction theory.
Yeah, they are ready now.
Okay. Okay. So today we discuss the functional central limit theorem. I will devote the first part of my lecture, but since it's very late, it will be probably we will not finish everything, but I will rush a little bit to try to isolate the important things. And this is very important. How do we pass from the traditional formulation of the functional central limit theorem to the modern formulation, which will involve test function? The modern formulation is very well suited to emphasize the analogy with quantum field theory, because in quantum field theory you have test functions. Okay, in classical probability what you use is an implicit test function, and what I want to show you is how this the presence of test function is implicit in the traditional formulation of the functional central limit theorem. So to illustrate this point, I will consider the simplest possibility. So instead of considering a vector valued random variable, you remember the index set D was labeling the components of a non-commutative vector valued random variable. Okay? Now we consider the case of a single random variable, so we omit the index of the upper index of the B. We have only one sequence of B. Moreover, for simplicity, in order to avoid the technical complication, I consider a single probability space. So let us say central limit theorem of Gaussian type rather than Poisson type, in which the expectation value doesn't depend on n itself. So we have a single probability space. The context is much simpler. And you see, what you change in the formulation, you put a t up. You sum not from 1 to n, but from 1 to the integer part of n times t. T can be arbitrary real number, positive, negative, it is not so important. Okay? To fix the idea, you can think in positive to begin, okay? Because usual Wiener process, you parameterize is Wt with t positive. So the standard theorems were done, functional central limit theorem were done for t positive. But this is not important. What is very important is that you have t here, but you normalize again with n. Of course, if you normalize with nt again, well, here the notation is not. I want to explain the notation. I have this. I want to explain the notation. This notation by definition means the integer part of t times the cardinality of n.
I think you could use 5 terms.
Oh.
With c up in the camera.
Okay, okay, okay. So the notation this is the notation we want to use. Okay. So with this notation, what we do? We want to rewrite this sum. Simply rewriting is an exercise. You want to rewrite this sum as an integral. Of course, since B doesn't depend on S, the integral at the volume of the interval n minus 1n is 1. Of course, this is a trivial identity, that this sum is equal to this, okay? And I integrate up to this sum. Now n is one-dimensional. Now I can, instead of integrating up to nt, I can put a characteristic function of nt and the summing over to infinity. Because when s will be outside this interval, this will be identically 0 because of this definition of the function. This is the characteristic function of the set. Okay? So when s is outside the interval down, the key function is identically 0. And now notice that you have that S belongs to nt if and only if S over n belongs to the interval 0t. So this allows us to, and moreover, this is what I said before, if S is large enough, larger than nt, this will be identically 0. So I can write a finite sum formally as an infinite sum with S over n. Notice I have here as this characteristic function is values in the real number. In fact, it has value in 0 or 1. But Bn belongs to A, to the algebra. So when we introduce now the normalization of the central limit, what we want to do? Instead of considering the traditional central limit theorem, it just uses this characteristic function. But you understand that very little will change if I fix a space of test functions and I replace the characteristic function by a test function. In the following, we will fix, I anticipate, this space T of test functions will be the space of functions with smooth functions with the compact support.
So in a way, all the algebras we are considering are real algebras. The Bn's we need to
Bn are arbitrary algebra. The Bn will satisfy the same conditions of the central limit theorem. So mean 0, we have not only an algebra, we have an algebraic probability space. I use the symbol expectation because you remember we need a little bit less than state for central limit theorem. But here you can think it is a state. And the Bn belong to A. Okay. So we want to study the asymptotics of these sums. So since f is compact support, I can bring the sum inside the integral if I put a characteristic function of the integral itself. This is trivial because this function has the support in 0, n. So we know that this sum is reduced to a finite sum. So I can, because f has compact support. And so I can exchange sum and limit for each fixed n, of course. When n goes to infinity, this will be different. So now consider this map for S fixed under this, with this definition. I am now integrating over S. So I get an element in the algebra. So we define a real linear map, which will associate to every f this element in this algebra. As I said, in the following, we will suppose first that they are a compact support. If they are also C infinity, they are automatically bounded. C infinity compact support, and they are obviously in L1. Okay? So we can, for the moment, we will not suppose smoothness. For example, why? Because we want a characteristic function. So we are not supposing smoothness. For this reason, this will be an additional assumption. Okay? If we take the usual space of compact supports infinity, this is a consequence. Okay? And so now we consider this n as a function of S. Before integration. When we integrate, we get an element in the algebra. But for each S, we have also an element in the algebra A. So we can consider as an operator-valued function, defined in the moment for S real, but then we will generalize. And so we have the central limit theorem. Central limit theorem, we want to study the asymptotics of these sums. I recall you these sums are this form. This form. Now, we want to get, as I said, the bridge. So we will replace R by RD. Okay? So we have to replace the intervals by some appropriate finite sets. For example, they can be square rectangles. Typically, one can take squares. But one can prove many theorems. Again, this is a technical point, but many theorems that essentially what kind of a family of sets that is increasing absorbing and absorbing all bounded sets and made a kind of a tessellation of RD, they will give it the same central limit. Okay? So now let us go back to the most general case. Now we will consider again vector-valued quantum random variable, in general non-commutative. So we put again the index Bj. I put a J, because not S as before, because now S we will use for time, for the element of RD. And now we want to prepare our central limit theorems. Will be, we want to prepare the ground for the quantum fields. So we will, if we have, you should think that for each fixed n, the Bnj are the generators of an algebra. See, the basic example we can take, let us take now B. J, the basic example will be Bjn is equal sigma Jn. And the algebra A will be a countable tensor product of 2 by 2 matrices, complex valued. Okay? And the sigma Jn, sigma j is plus 0 minus, and you have the sigma plus will be and sigma minus the adjoint of this. See, this is for each, for inside the single factor of the product. When I have the index n, it means I am considering the natural embedding, which puts the sigma plus, for example, into the n factor and identity everywhere else. Okay? So this is the natural embedding, and so this will be the quantum analog of a sequence of Bernoulli random variable. And then you will form the central limit theorem, the central limit sums 1 over n to the 1/2 of the sigma, and here you put the index epsilon. Epsilon will belong, or j, for example. No, j we will use for the sum. And you sum from n1 to capital N. And this will converge to creation annihilation, and this one, the diagonal, will go to the number operator. Okay? So we are preparing a generalization of this situation. When you have test functions, to introduce, to go from test functions to the, from the single random variable, like in this framework, to what we are doing today, the functional central limit theorem, corresponds to the transition, for example, A plus minus to A plus minus F. These are the famous quantum fields. In this sense, I say functional central limit theorem, like a single central limit theorem, go to standard quantum mechanics. This is the second quantization process. Second quantization in the probabilistic language means passage from usual central limit theorem to functional central limit theorem. In this transition, one new element, which is essentially analytical, will appear. And all the goal of my lecture is to explain to you what is the new analytical element, what do we add, what is the additional difficulty that we have when we pass from single random variables to test function. This is what I want to explain today. So this, now you understand what is this partition of the set. This partition corresponds to plus, 0, and minus in the simplest but most fundamental example. Okay? And this condition, you see, that this is J. You should read J, this S0. Okay, this is still correct. You can. What does it mean, this notation? You see, look again in this situation. When I take the adjoint of S plus, so I will obtain S minus. And when I take the adjoint of S0, I obtain itself. So this means that in the language of this, that plus star equal minus and 0 star equal 0. Okay? In the this is the rule of by which I define this J adjoint. When J belongs to D, to the set D. Okay. We have a space of, now it's important to the family that we take. in one dimension, this family I is simply the family of all intervals. The simplest possible, the one-sided central limit theorems. It's convenient to have a partition. Okay, so that clearly you have that if you take the union of all I in script I, you get n. And with this notation, you have this, if they are different. Of course, if they are equal, they coincide. So we do this assumption. Moreover, we want that the diameter is bounded, uniformly bounded, for this set I. So in some sense, let me take these sets. This will be more correct. Okay, in this case, you have the diameter is constant is equal to 1, and you sum over unions of these intervals. Okay, this is more correct. So in that example, the constant c is equal to 1, and diameter is the diameter in Rd with respect to Euclidean distance. This is a small generalization, but it can be used when you want to do central limit theorems which are not concentrated on R. For example, the standard central limit theorem in classical probability, or this example is not the analog of Rd, because the analog of Rd would be Zd. So since we are taking Nd, this is the analog of R plus D. As you see, R plus is a cone. It has a very important property that we will use in the end. Cone means that, let us say, C contained in Rd is a cone if the sum of two elements in C is in C, and for every positive lambda, you can also put greater in, this depends on the definition, open cone or closed cone, the lambda x is in C whenever x is in C. Okay? This is the definition of a cone. We will use this property, in fact, a little bit less. So now we fix an element in the set D plus union 0, because that is why we take a real valued map. Remember that in the case of quantum field, the map which to a test function f associate a daga f is linear. Okay? But you know that AF, which you can call A minus F, is the A daga F conjugate. And so the corresponding map must be antilinear. The annihilator map is antilinear. For this reason, we separate this map, and F appears linearly in the plus and the 0 case. And then we define the minus case as the adjoint of the as I said, and so the adjoint comes here. The adjoint of F is the conjugate by definition. And here, remember, the example of the index that I did with the Pauli matrices, you have the conjugate index, J star, which is uniquely defined because the set of generators is self-adjoint. And then we also introduce this notation which will simplify our life for central limit theorem. So Fj will be Ft if the index is in plus 0, and F conjugate if the index is in minus. So you see, what, what is the new point? You have now still elements in the algebra A. However, now, because of the dependence of the test function, this element depends also on capital N. And this was not true in the standard central limit theorem, a moment central limit theorem, as we did. There are central limit theorem in quantum probability in which you have dependence of two indices, and these are the famous triangular arrays. Okay? So, of course, if the Bn have zero mean, also this integral will have zero mean. Because remember, B doesn't depend on T. Only the function depends on T. So it's a 0 times a constant. And so, if we want to have the formulation of central limit theorem, what will be the new mixed moments? Which means the mixed moments for this n-dependent random variables, quantum random variables, these ones. You will see that the mixed moments will have this form. Well, this is, sorry, I did not. Well, but what is important is that when you have a majorization in modulus of this will be less or equal. These functions, by assumptions, are bounded. So I say all this because you reduce to the, if the Bn satisfy the condition of uniform boundedness on moment, then also the generalized, the test function dependent Bn will satisfy the same boundedness condition. So we can apply the central limit here. And well, no, we cannot apply what we already did because the Bn depend also on capital N. And now we want to show how we have to change. In order to show this, I will consider the simplest possibility when we consider only second moments. You remember, the convergence of the covariance was a necessary condition, and is also a necessary condition for the functional central limit theorem. So let us examine from the examination, the analysis of the covariance, you will understand what is the additional analytical result that we need to establish the functional central limit theorem. So let us begin to see the covariance. We assume that well, I will make a stronger assumption than the limit exists. This assumption was done in the central limit theorem. But in the following, we will do the following simplifying assumption. We will do the stationarity assumption that E of B J N B H n is equal to some c of, well, in fact, we can, stationarity, we can say equal E of B J0 B H0, where 0 is, now we are in Rd, so 0 is the 0 over D. So under this assumption, what we have? We have that the limit of the covariance will correspond to this limit. Okay. Pay attention. In the covariance, we have the sum here. So we have two integrals, you will see during the proof. But in the limit, we have only on the same integral on the diagonal. This is the delta function. This is what we want to prove. Okay? Why the delta function? You immediately see that, and the delta function will be related to independence. Because if the F1 and F2 have this joint support, the correlation of these two is 0. But you know that the limit you expect will be a Gaussian process. And you know that for a Gaussian process, two random variables are independent even only if they have 0 covariance. Okay? And this is the definition of white noise.
So probably also follows from here, right? If you take two random variables, the sum and minus are independent from here. If you take two random variables, x and y, if x plus y is independent of x minus y, then also you can say x and y are both Gaussian.
Ah, there is a, yes. There are also in quantum.
There are many ways
Yeah.
to interpret
Well, there are many characterizations of Gaussian in this. One of the characterization, for example, was
It's mainly because of the scaling.
yeah, but here we are not taking the sums of the generators. We just consider the generators. Okay, so let me show where the difficulty of the proof is, and then we separate analysis from algebra, and then we prove the analytical theorem. Okay. So, compute the covariance. The covariance, by definition, is this one. This is the sum, the central limit sum. So we have the normalization. And now, remembering that the sum was correspond to the integral and the sum, I sum over n, and I integrate over the argument of the test functions f1, f2. So if you remember what we have written before, we have 1 over the cardinality of n here. Then we have an expectation of the covariance at the A level, algebra level. And then we have, I have isolated here. In fact, you can bring this integral inside here. I put here because it doesn't fit in the screen. Okay? So you can put these two integrals here, and you are separating the algebraic part and the analytical part. And you want to show that this converges. Now, you see, now we use the singleton condition at the algebraic level. The singleton condition will be crucial because when the n1 is different from n2, they are both singletons. So they give 0 contribution because they have mean 0 by assumption. So I reduce these two sum to a single sum on the diagonal. Okay? and I obtain this. And now I use the stationarity assumption, which we had not in the central limit theorem, but I want to simplify the algebraic part in order to single out the analytical part in more evidence. So we do stationarity. With the stationarity assumption, we can bring outside you see, we have this sum over n, and here is n. But with the stationarity assumption, this covariance will not depend on n. And so I can take this expectation and bring it out. In fact, I write like this. And now you see, and now we want to normalize. We have this integral, and of course by change of variable we change t over n, but then an n will appear here. In fact, cardinality of n, this is a misprint, okay? It's the cardinality of the number n. This is true in one dimension, okay? So do you use this elementary, just change of variable, and you see each of these two integrals will give a factor n, but I have 1 over n here. So what I come out is an n, a single n, because n square will come from this change of variable. But 1 over n is the normalization. And so I remain with this. What is the advantage of the change of variable? Well, let us see the final result. The final result is that, you see, I am using now that t over the cardinality of n is in this characteristic set, in the set In, if and only if t is in the characteristic set of In divided by n. And so we finally arrive. We have now singled out. You see, you have this integral, but you have this expression here. And this limit is the new analytical point with respect to the standard central limit theorem. So when you do functional central limit theorems, you have to prove this. But you recognize intuitively, if you have a little bit of familiarity with the distribution, that this will be an approximation of the delta function. So, this is our conclusion. The covariance of order n will be a number, a factor, and then this limit. So we are led to study this quantity. And here, just I want to do the analogy. I told you there is some analogy with stochastic limit. And the stochastic limit, this lambda, is a coupling constant. That is why people speak of weak coupling. Stochastic limit is a kind of central limit theorem. Okay? So, when you put this lambda like this, you obtain this term here. And now we want to prove the fundamental result, analytical. Now we need some analysis, because we want to study this object, which is, you see, this object here, you can consider it as a delta lambda, which intuitively is a kind of approximation of delta function, which gives a linear functional on the, you see, the dimension 2, because now we have two variables, t1 and t2. So that is why is not the Schwarz space on the doubled dimension. So it's not the delta function on the Schwarz space. Is the delta function, how to say, promoted to a function of two variables, delta T1 minus T2. So first we use an estimate. We prove the following. We fix n and we fix lambda. And we fix the functions f1, f2. Now we take compact support, continuous. We need continuity. Okay? In fact, here I take even in the space of C infinity. We will not use in this theorem C infinity. So I emphasize this because it is it means if we only use continuity, when we fix the interval I, we can also have characteristic step functions. So the theorem, the lemma we want to prove that essentially the integral over two variables is the same as the integral over one variable up to a small error. The error is small for two reasons. First, because this epsilon is small. And second, because this in is not so small, but lambda will become small. Remember, lambda is 1 over n. So, how to prove this? Just as I said, we only use the uniform continuity of the fact of the functions that we are considering f1, f2. So, since because they are uniformly continuous, whenever I have two S1, S2 in the support, and they are not very far, then this can be less than epsilon. So I give epsilon, and then I fix delta so that this implication is satisfied. Then I will write this integral of the product as you see, I have here added and subtracted just f1, s2. So here I add and subtract s1, s2. And I obtain this difference. Now notice that f1 over s2, this is integrated over the two variables. And I am assuming that this has a measure less than a constant. We can take, for example, the Lebesgue measure of each in equal to 1 as a condition. The Lebesgue measure remember, in typically is the interval. This is the example. So, in using this, I want to attract your attention on the fact that there is the factor 1 over lambda here, so that when I when I integrate over ds1, this will give me 1 lambda in, but the Lebesgue measure of in is 1, and the lambda will simplify with the 1 over lambda. This is the point. So you see why the lambda now disappears from here, but still he's there. And now you use the majorization. So I use Fubini theorem and the then I am using the fact that this diameter is less than c, and I use the fact that the distance is less than what for every uniformly, since the support is in this set in and the diameter of the set is c, it means that if I take 2 arbitrary points of set inside the set, their distance, I have to finish. There is another seminar. Okay, so I think but I mean.
We have 5 minutes still.
5 minutes.
But oh no, it's already over.
Just
It's
10
past 11.
10 past 11.
He has to go.
Yes, go.
You have to go.
Okay.
He has to go with his camera.
Aha. Okay. So I think we can without him.
Well, we can continue without him, or you can stop now.
Just finish. Just 1 minute. 1 minute.
Okay.
Okay, 1 minute. Because we are at the end of this theorem. You see. So since lambda is very small, it means that this distance is small. So I can apply the majorization with epsilon, and this is the end of the proof.
Yeah.
Okay? And so we proved the main lemma. From the lemma, we will get the convergence to the delta function. Okay? That the limit is the delta function of the set U that we introduced before, the union of all IN.
Okay, you can stop.
Thank you very
He has
much.
to stop because he has to.
Thank you.